Hello student, in this lecture I will discuss about graphs for the term 1 by 1 plus j omega t, that means normal pole. So see, the magnitude for the term 1 by 1 plus j omega t in decibel is given by 10 log 10 mod of 1 by 1 plus j omega t, and this is equal to 20 log 10 1 divided by root under 1 plus omega square t square. So from this equation we can write minus 20 log 10 root under 1 plus j omega square t square. Now consider these two following cases. So first case is omega t. If omega t is very greater than 1, that means at very low frequency omega t is negligible as compared to 1. So if omega t is negligible as compared to 1, then the magnitude is 20 log 10 1 by 1 plus j omega t, and this is equal to minus 20 log 10 1. This is equal to 0 dB. And if we consider the second case, in second case omega t is very greater than 1, that means at very high frequency. So in that case 1 is negligible as compared to omega t. That means the magnitude 20 log 10 mod of 1 by 1 plus j omega t, this is equal to minus 20 log 10 root under omega square t square. This is equal to minus 20 log 10 omega t. And so this is, from this equation we can write minus 20 log 10 omega plus 20 log 10 1 by t. Okay, so in view of equation 7.58 and 7.59, graph for case 1, case 1 is if omega t is very less than 1, that means at very low frequency omega t is negligible as compared to 1, then that case our magnitude is 0 dB. Okay, and in for case 2, when omega t is very greater than 1, that means very high frequency, 1 is negligible as compared to omega t. So in that case our graph has a slope of minus 20 dB per decade. Okay, so see these two graph, that means one graph is 0 dB for case 1 and another graph have minus 20 dB slope. This is 20 dB slope. Okay, let me clear this. So see, these two graphs intersect on 0 dB axis at a point determined by equating right hand side of equation 7.59 to 0. Okay, so if we equating the right hand side of equation 7.59 is 0, then we find omega equal to 1 by t. Okay, now here see the two graphs intersect on 0 dB axis at omega equal to 1 by t. Now the graphs for cases 1 and 2 are shown in figure 7.18.4a. Okay, now we see the graph for phase angle. The phase angle for the term 1 by 1 plus j omega t is given by phi equal to minus tan inverse 1 omega t divided by 1. Okay, so phase angle phi equal to minus tan inverse omega t by 1. So if we consider at very low frequency, that means when omega t is very less than 1, then in that case phi equal to minus tan inverse 0, that means phi equal to 0. Okay, and at omega equal to 1 by t, phi equal to tan inverse 1 by t dot t, that is tan inverse 1, that means phi equal to minus 45 degree. and at very high frequencies omega t is very large, and in that case phi is equivalent to 10 minus 10 inverse infinity, that means phi equivalent to minus 90 degree. Okay, so the graph for phase angle is shown here. Okay, so see, if when omega t is very small, then phi equal to 0 degree. This when omega equal to 1 by t, then our phi equal to minus 45 degree, this one. And when omega t is very large, that means very high frequency, then phi equal to minus 90 degree. Okay, clear these things, minus 90 degree. Okay, so the graph for phase angle is shown in figure B. Okay, so see the magnitude versus log 10 omega graph shown in this figure. 7.18.3 and 7.18.3 means this graph, and 7.18.4. okay, so the magnitude versus log 10 omega graph shown in these two figure for normal pole and for normal 0. Okay, for the term 1 plus j omega t, this is normal 0, and for the term 1 by 1 plus j omega t, this is normal pole, and these are asymptotic plots. A comparison of asymptotic plot and exact plot. So there is some comparison between asymptotic plot and exact plot. Okay, so the exact plot is shown by dotted line. Okay, the exact plot shown dotted line. The exact and asymptotic plot match each other at frequencies lower and higher than omega equal to 1 by t. Okay, and the frequency omega equal to 1 by t is called corner frequency, and the maximum error between the exact plot and asymptotic plot occurs at corner frequency, and the error is calculated for asymptotic plot, and there is some formula we have used for calculating the error between exact and asymptotic plot. Okay, so this will be discussed in the next lecture. Okay.